Let's start this Prism video with a recap and expounding on some of the stuff we talked about in the first video. So we know that Prism can be ground into the lenses, and while it's not evident when we look at the glasses themselves, it becomes evident when we look at them through the lensometer, and we can't center them that they must have ground in Prism. And we know that Prism can be induced by decentering. That's when the optic centers of the lenses don't align with the patient's visual axis. So it's very important to know where your patient's visual axis is. That means know your patient's PD and measure where the optical center is on the lenses when you read them on the lensometer. Because if the two don't line up, our patient is experiencing a prismatic effect through his glasses, whether it's intentional, prescribed, or non-intentional, accidental. We also know that the farther away from the optic center, the greater the induced prism. Did we talk about that? Yes, we did. Prentice's law, or Prentice's rule as it's often called, C is the distance away from the optic center. And if we were to keep D, the dioptric power, the same, as C gets bigger, P gets bigger. If D is 1 and C is 5 centimeters away, then P is 5. If C is 6, P is 6. If C is 7, P is 7. So the farther away, the more induced prism. And it also follows what? The greater the dioptric power, the greater the prism. Anisometropia is when the eyes have different refractive power by at least 1 diopter. Some books say 1 diopter, some say 1.5, some say 2 or more, so at least 1 diopter of difference between the two eyes. And that can be caused by, it can just be congenital, it can be caused by cataracts, it can be caused by trauma. Antimetropia is basically the same thing, but one eye is myopic and the other eye is hyperopic. So one eye requires a minus correction, the other one requires a plus correction. Anisoconia is a problem that can be caused by anisometropia or antimetropia. Anisoconia is when the sizes of the retinal images in each eye don't match up. For instance, in this case, the patient has a correction of +1 in one eye and +4 in the other. Now, we know that plus lenses magnify an image and minus lenses minify. So the +1 lens will magnify a bit, but the +4 lens will magnify much more. Now, our brains confuse together images that are slightly different, but not that different. And here we have the same object, the houses, but this time the patient looking at them has a -1 lens, which minifies the object, and a -4 lens that minifies much more. So this patient is experiencing retinal images that have a significant size difference. So in both of these cases, the patient would most likely be experiencing diplopia. The brain is unable to fuse these two images into one. Anisoconia can be corrected with special lenses called isoconic lenses. They can magnify or minify the image size so that the images can be made a little bit more uniform. They're very rare nowadays, though, because there's so many other options: contact lenses, refractive surgeries. Anisophoria is a heterophoria that's present only in certain directions of gaze. For instance, you break fusion to try to tease out aphoria, and it's only there when the patient is looking down, for instance, or it's only there when the patient is looking up. When they're looking straight ahead and you break fusion, there's no phoria. Anisophoria can be caused by the corrective lenses the patient is wearing, in which case it's called optical anisophoria. What happens is the spectacle correction is fine if the patient's looking out the optical centers of the lenses. But when the patient looks through another part of the spectacle lenses, for instance, when the patient is gazing down, for instance. The image would either be displaced up or down, depending on whether the lens is convex or concave. Well, that's no problem. But remember in the first Prism video when I said that the apical angle, the angle at the apex of the prism, is a determining factor in the amount of deviation of the light rays? Okay, well, we have lenses with two very different size apical angles with these two lenses. So they are going to do very different things as prisms. So what we're going to have is an object that is displaced to one location in one eye and a different location in the other eye. And that can cause a problem. Some of the things that a patient with anisometropia or antimetropia or anisophoria might be experiencing could be, I think we mentioned diplopia, asthenopia, which is a general catch-all term for, could be headaches, dizziness, eye strain, eye aches. Now the treatment, I think I mentioned refractive surgery, contacts, isoconic lenses, and slab off. The symptoms are going to vary per patient and for some other reasons. For instance, let's say the patient has had this anisometropia all their lives and now they're 40 years old. Well, by this point, they have probably learned to live with it and probably are experiencing some suppression so that they don't experience diplopia. Sometimes patients just adapt. As far as slab off is concerned, and I'll explain that in just a moment, the biggest issue is when these things come on suddenly, such as cataract surgery. When you have a patient who was, let's say, a +4, now they've had cataract surgery in one eye, and that eye no longer needs any correction. They're a plano in that eye. So they have a plano in one eye and a +4 in the other eye. That's going to cause a problem for that patient who is not used to it. When we're talking about looking above or below the optic center, we're talking about vertical imbalance or unequal vertical powers in these two very different powered lenses. With a patient who is wearing single vision lenses, sometimes they can adjust just fine by moving their head up and down so that they're always looking through or very close to the optic center of the lenses and not experiencing a lot of induced prism that way. But when a patient is wearing multifocal lenses, and that's what that protrusion at the bottom of the lenses is supposed to be, a bifocal segment, when a patient's wearing multifocal lenses, they're forced to look through that prism away from the optical center. And that's when we have a real problem with vertical deviation. One way to correct this is by introducing a base-up prism in one of the lenses. And this is done through a process called bicentric grinding or slab off. And slab off is put on the one lens of the two that is the most minus or the least plus, which are, try to think of those as the same thing, the most minus and the least plus. In other words, which one of these two lenses is the most minus? It's going to be the one that's the least plus. So of these two sets of lenses, the lenses that are circled would be the ones that get the slab off. So when base-up prism is added to the most minus lens, this is sort of what happens. They sort of match up with one another. Now this is not how it's done. In reality, they don't slap a base-up prism right on top like that so it's sticking all out and everything. This is just a picture to keep in your head if you're trying to remember this. The plus lens is easy to understand. It's pretty straightforward. With the minus, I just wanted to point out with this picture, the ones that are highlighted in yellow, the prisms cancel one another. One's face up, one's face down, and they cancel one another. Same thing with the dotted one on the other side. It's canceling a bit of that base down prism caused by the minus lens. Okay, this is how slab off is actually done on a plastic lens. The power is ground onto the back of a plastic blank, and that blank already has the bifocal power there on the front. And once that power curve is made, we have an optic center there where the arrow is. Now, the slab off part, another curve is cut, the red one there, down at the bottom, and that section in yellow that is to be removed, look what that is. That's a base down prism. So when the base down prism is removed, that leaves a base up prism. And that red curve has its own optic center. So the lens that is left has two optic centers, hence the term bicentric. Now, there's also something called reverse slab off, and I'm not going to go into a complete explanation because basically it's just the opposite of slab off. It's put on the most plus, least minus lens, and it is, instead of base up prism, it's base down prism. Okay, I'm just going to toss in a quick slab off problem so that you can test your understanding of the concepts. It's an easy problem, and I'm not going to put the answer here. You'll find the answer and a short explanation at the end of the video. So here's the problem. If an antimetropic patient wearing a prescription of +2 spherical in the right eye and -2 spherical in the left eye is complaining of vertical diplopia when reading, and both of the patient's eyes are focusing approximately 5 millimeters down from the optical center, how much slab off should this patient be prescribed, and in which direction, and on which lens? Okay, slab off is written in terms of prism diopters. And again, the answer's at the end of the video. Okay, I'm going to talk for a minute about image jump. What is it? Well, these are bifocal glasses, and the lenses are minus lenses, and the bifocal, of course, is always plus the add power. How do I know they're minus lenses? Well, you can see at the bottom that the stem of this bouquet is blurry, and then at the top, the bouquet is a little bit minified, whereas through the plus lens, the bifocal, it's a little bit magnified. Image jump happens when vision goes from one lens with its optical center to another lens with its own optical center. Now, it doesn't matter that we have a minus lens here with a plus reading add dye. They could both be plus lenses. The image jump is due to the difference in displacement of the objects that each lens provides. Okay? It's due to the difference in displacement provided by each lens. Now, remember when looking through the optic centers of a lens, there's no displacement? Displacement is an effect caused by prisms. So, as an eye is traveling from one optic center, as it moves away from that optic center to the other, we're going to have prismatic effects caused by both. Because anytime you're away from the optic center, there's prismatic effects. So the eye will experience, going from one optic center to the other, the eye will experience the prismatic effects induced by each lens, and it makes the image look like it's jumping. That's why it's called image jump, because it looks like the image jumps. And I'll show you how that happens. Now this, let's say that this was a plug that we're going to make a bifocal out of. And that black dot there is the optic center. And in order to make a bifocal out of it, we have to cut the bifocal out of it. Now we're going to make a round top bifocal, a cryptoc. Now this bifocal plug is a plus lens. It's a plus lens with its own optic center. Now, and I put a cross section there. So you can imagine it as two prisms base to base. And where we're going to cut it to put it into the patient's eyeglasses, we're going to cut it above the optic center there, which is the black dot. And cross section here, you can see that that is where the red dotted line is, and then we're discarding the portion below the red dotted line, the one with the red X. We're discarding that and we're using the top. So when we put it on the patient's glasses, as the patient's eyes move from the distance vision down to read something, down into their add power, they're going to hit what was essentially the top of this round lens. And remember what we said about prism, the farther you get away from the optic center? That was C in our equation. The patient is going to hit maximum amount of prism as they enter the reading add power of their bifocal. And for a flat top bifocal, well, you're still going to hit prism, but it's not going to be quite as much because it's not as far away from the optic center. Probably the best lens for avoiding the image jump, would be the executive bifocal. That goes all the way across the lens, but you see where it's cut? It's cut right across the optic center. And it's put on the distance lens right at the optic center. So you have two optic centers touching. So when the patient goes from distance to reading, they really don't hit prism at all. Of course, the progressive lenses wouldn't have it either. So the executive and the progressive multifocals would probably be the best to avoid image jump. Now, there's a lot more that can be said about bifocal styles and image jump, and I'm not really going to do it in this video because I don't think it has its place here. There's just too much to cover in one video, so maybe another video talking all about bifocal styles might be appropriate. A Fresnel prism, which was created or discovered by a French physicist named Augustin Fresnel, he figured out that a series of very small prisms could actually replace a larger prism. And now we make Fresnel prisms that are paper thin and can be adhered to the back of a lens, an eyeglass lens. And here is our model, Hillary Clinton, modeling a Fresnel prism. And you can see that it's very obvious when somebody's wearing one, which is probably why we don't see more people wearing them. Also, it's temporary because it's not going to stay on forever. It's just stuck to the lens and you can actually peel it off. So it's used as just a temporary solution to for the patient to avoid diplopia. The prism reference point describes the point on the lens where the prism occurs. Now, we talked about base in, base out, base up, base down prism, but prism, as we well know, can be in more than one direction. So what if we have 3 prism diopters base up and 5 base in? How do we know how much prism that is, or where it is? Just a side note before I explain this, don't worry about the math here. I'm going through it just so you can understand what this means and have a background knowledge. You don't really need to write down the formulas or understand how the math is done. You just need to know basically what this is. Okay, to figure out where the PRP is, we're just going to plot our prism on a simple graph. We know where 90 and 180 are on the graph, and to orient we need to know where the nose is, so we know which way is in or out. Okay, to start plotting this, to find out where our PRP is, we're going to go up 3 from center, because we have 3 base up, and then we're going to go in towards the nose 5 because we have 5 diopters of base in. And that's our PRP right there. But where is that? Where is that from center? To find out where that is, we have to draw a line and make a right triangle out of it. One side of that triangle would be 3 units long, and one side would be 5 units long. And since it's a right triangle, we can figure out what the long side is, the hypotenuse. Remember, a squared plus b squared equals c squared, the Pythagorean theorem? And we just plug in the numbers, solve, and we figure out that the length of the hypotenuse side is 5.8 units long. So this can be written 5.8 prism diopters base up and in. But that doesn't really accurately describe where our PRP is yet, because with that we could have 5 up and 3 in rather than 5 in and 3 up. So we either have to write 5.8 prism diopters, 5 in and 3 up, or we could specify the angle measurement. How to figure out the angle? Well, remember when we did sine of an angle? To figure out this angle, we're going to use the tangent. And the tangent is the opposite over the adjacent. The line opposite that angle is 3. We're going to put that over 5, which is adjacent to that angle. And that leaves us with 0.6. Now, to get from 0.6 to an angle measurement, we have to take the arctan, the arctangent, which is the reciprocal of the tangent, or 1 over the tangent. And you just plug that into your calculator and come out with approximately 31 degrees. That angle is approximately 31 degrees. Now we can say that we have 5.8 prism diopters base up and in at 31, or we can say 5.8 prism diopters at 31, because if it's at 31, it would be up and in. Do you need to know this? Do you need to know how to figure it out? Highly unlikely you would ever need to know this. But if you see it written that way, at least you'll understand what that means. Now the answer to our slab-off question. The answer is 2 diopters of base-up prism placed in the left lens. The right eye will have an induced prism of 1 diopter base up, and the left eye will have 1 diopter base down. Slab-off is always placed on the most minus lens, and slab-off provides base-up prism. And here's a quick explanation and a visual of that.